Hi there, YouTube. So today I'm outside the University of Sheffield's Engineering Heart Space. One of the labs here is a wind tunnel lab. So I'm supervising a final year project student who's doing his master's project and is trying to quantify the parasitic drag of various components of the glider. So control frame effectively, so uprights and also the wires. Right, so here we are in the wind tunnel lab in the Department of Mechanical Engineering in the University of Sheffield. So you can see the wind tunnel behind me. So the basic principle of a wind tunnel is pretty simple. You've got this end where the air gets sucked in through this grid, which if you look close you can see is an aluminium honeycomb. So the purpose of this is to straighten the air. Now coming down the side of it, you can see you've got a big cross-sectional area which is constricted down into a smaller cross-sectional area to accelerate the flow, and then at the back of it you have a nice juicy fan motor which is sucking the air through. So you pull the air through the working section so that you have smoother flow inside the working section. So this is the sort of standard open wind tunnel layout. What you might have on a higher powered wind tunnel or a higher speed wind tunnel, you'd actually link, like a racetrack, you'd link the exit round in a loop to come back round to the entrance, so that you accelerate the air round and round a racetrack. So for getting up to higher speeds and not using quite so much power, that's the way to do it. In this case, it's just sucking the air in from the front, blowing it out the back, so it all gets quite windy when it goes fast. So of course this also means that we do have to make sure that nothing gets, there's nothing that's going to get blown away behind it when we turn it on. So this is it running at maximum, the highest speed we're going to do. So that's going at 50 miles an hour inside there. So here's the student who's working on this project. So his name's Will, and if you want to introduce yourself, Will.
Hi, I'm Will. I'm a final year aerospace student at the University of Sheffield, running some wind tunnel tests, looking at the difference in performance of different hang glider components, looking to see if we can use mesh turbulators to potentially get some performance gains in terms of the main spar, and then analyse the difference in drag of the different control sections between your metal-backed aerofoils and your rubber to see the performance improvements that we can make.
Yeah, and how are you finding the degree? And you did this year in industry as well.
Yeah. I spent a year abroad, away at the BAE, up in Preston, working up there, so that was good. Back at Sheffield now for the 5th year now. It's great at Sheffield. The facilities are amazing. It's nice to be able to get into tunnels like this.
This project is being co-supervised by Dr. Simon Hayes here, so Department of Aerospace Engineering at the University of Sheffield. He's a senior lecturer here. So Simon, do you want to say a little bit about the university and about student projects like this one?
Yep, so we have courses in aerospace engineering at undergraduate and MSc level here at Sheffield. And as part of the courses, the MScs, the BEng, the MEng, students have to do an individual investigative project that allows them to explore their subject matter, in this case aerospace engineering. And it's really good for us to find them projects which are in relation to industry, as it allows the students to understand where their work fits into the industry as a whole. So being able to collaborate with a company allows them to do real work that has direct relevance to their future careers, and in this case has allowed us to look at fluid dynamics and practical wind tunnel testing, but it might include computer modelling, it might include materials testing, it might include electronics as well. Anything that really allows the students to get to grips with aerospace engineering. And so this is an ideal opportunity to do some cutting edge research that also has a potential practical benefit.
Yeah, and obviously it works very well for us as well because we're getting some use on this wind tunnel, and we're supplying materials, things to test, giving some supervision, some guidance as well. And yeah, I did my undergraduate and my PhD here in Sheffield, and in fact Simon was one of my lecturers for my undergraduate and also around and helping with my PhD as well. So we go back a long way. So often when you're doing wind tunnel testing, for example, if you're trying to get the, if you're trying to test for the whole aircraft in a wind tunnel, then obviously you can't normally put the whole aircraft in a wind tunnel, so you have to do some sort of scaling. So you have to use a smaller scale model for the test. But then that then runs you into the problem of speeds. So you need to be running at the correct speed to be representative, and so normally that means trying to match the Reynolds number as closely as you can, but then you might also have Mach numbers. So if you're trying to match Reynolds and Mach numbers together, then that might mean that you need to use a wind tunnel which can be pressurised or depressurised so that you can match the conditions as well as possible. Now, in our case, of course, we're quite lucky because we're actually testing the actual components in there, which means that by definition they're one-to-one scale, and we're running the wind tunnel at the kind of speeds that hang glider actually flies at, and so it's fast enough to be representative, and the parts are the actual parts, so there's no need to apply any scaling factors in this place. Now obviously we also need to measure the forces on it, so we have our 6 DOF load cell, so 6 degrees of freedom, so that's able to measure forces in all 3 dimensions, so up, down, backwards, forwards and sideways, and it's also able to measure the moments or the twisting, the torque around all 3 of those axes as well. So if we were testing like a model of an aircraft in here, we'd be able to measure the lift, the drag, any side slip type. We'd be able to measure the lift, the drag, any side slip type moments or side slip type forces, and we'd also be able to measure the moments, so pitch, roll and yaw moments. Obviously for this, what we're doing at the moment, we're only really interested in drag, so we're only really caring about the force in the flow direction. Obviously it's not really generating any lift, there's not any sideways force on it, and we don't really care about the moments either for this purpose. What you can also see there is a pitot tube, so that's measuring the speed in the tunnel, so that we have the actual airspeed for each condition we're running. So it's been a couple of months now since those video clips were recorded. Will's finished his project now. He's written up his thesis, submitted it. Hope he gets a good mark. He did really good work on this project. He's sent all his data over to me, so I've been having a look through it now and starting to crunch numbers. There's some really good data there actually, so we'll go through it now. As a reminder, what we were trying to do, we were trying to get the numbers for the amount of parasitic drag being generated by various bits of the glider. So we wanted to do the uprights, the wires, and then for a single surface glider, the cross tube as well we were doing. So we got really good data for the uprights. We didn't manage to get anything for the wires. It's tricky to measure because obviously the forces are low and you need to hold the wire under tension. So the frame that we were using to tension it was just generating too much drag itself. It was getting buffeted around in the wind, so the force was sort of bouncing up and down all over the place, and you just couldn't detect the extra force that a wire was giving, let alone tell the difference between different types of wire. So, but potentially that is one for a student to have a go at next year. It will be an experimental project of trying to build a rig to be able to measure these lower forces. I'd like to really dig into and quantify exactly how much difference these different diameter side wires actually make, and also the effects of the surface texture, because there's quite big differences between plastic coated or uncoated, but then also between the different actual like wire builds of number of strands and so forth. And at these small scales, the surface roughness and texture should have an effect. So it'll be an interesting thing for a student project to do next year. Also, another thing we were trying to do with this project was that I had an idea for trying to reduce the drag on the cross tube on a single surface glider. Now, I know it's sort of not exactly that important to be trying to reduce the drag on a single surface glider, which by definition is a low performance glider. So is how much do you really need better performance? But then the idea was that if it was a quick, easy, cheap way of getting like a free performance gain, then why not? So we had a go at that as well. So we got some interesting results from that, and I'll share those in a future video. Actually, that's one we can discuss in more length. But yeah, as I say, on the uprights we got really good data, and on the wires we didn't get any data. But let's go into the stuff on the control frame on the uprights a bit more now. We're comparing 3 different profiles for the uprights. So we're using a round cylinder as a baseline. We don't actually make gliders that have round uprights anymore. Our standard is the rubber backs now, but it's a good baseline to use, and also because the round base bar we do use with the rubber backed uprights, so we need to know the drag for that as well. We have the rubber backed upright section that we're going to be testing, and we have the speed section which we're going to be testing. Now, the speed section was originally developed by my predecessor, and he did use a wind tunnel for that to get the positioning of the turbulator strips, so that should be the best one. So let's just confirm that. Also, just as a quick recap, what these terms mean. So I'm talking about drag. So drag is a force, and in this context I'm going to be talking about drag per meter. So that's per linear meter, per meter length of the tube, how much force in newtons is being exerted on that at different speeds. I'll also be talking about drag coefficient, so CD as it's also known. Now, the force is directly measured by the load cell that I showed earlier. The CD we have to calculate, but we know the speed because that's being measured in the wind tunnel as well. And then the other thing we need to calculate is that it's relative to a reference area. So for these purposes, as a reference area, I'm going to be using the cross section that's exposed to the airflow. So that's a 1 meter length multiplied by the width of the upright. So it's not the total area of the upright, it's not sort of if you look at it sideways or anything like that, it's the cross section that's exposed to the oncoming air. So if we look at the coefficients of drag first, so it's quite interesting. So the first thing to note is that the drag for the cylinder is a lot higher, so for the round shape it's much higher than for the 2 aerofoils, so that's what we'd expect, but it's good to see that as well. It's also quite nice actually that the value for that cylinder is 1.17, which actually measures almost exactly the textbook value of what it should be, so that's also quite reassuring to see. What we can also see is that for none of these shapes, the drag coefficient isn't constant as a function of speed. So just to reiterate, this is the drag coefficient, this isn't the total drag. So when you see the drag coefficient dropping, it doesn't mean it doesn't mean you're getting less drag as you go faster, it means that this coefficient is falling. But you can see it isn't a constant across the speed. For the cylinder it's reasonably constant, but for the 2 aerofoil sections, it actually has this peak at low speed and then it drops off and flattens out, so that's nice to see. It's sort of I think what's happening there, it's showing that those turbulators, so those tiny little strips that if you look along the front of your uprights, if you've got aerofoil uprights, look along them and you'll see these tiny little ridges. They're not very high, but what they're doing is they're tripping the airflow. So as you start to increase the speed, so at the very low speeds, now it's very difficult to sort of measure down this low, but you'll get a smooth flow around the shape. As you start to increase the speed, you'll get turbulence starting to build up, large scale turbulence. If you get above a certain speed, then that turbulence starts to collapse and wrap around more, and the turbulators can make that happen at a lower speed. So that's probably what we're seeing there, is why that's dropping off like it is quite soon, is because the flow is, although it's turbulent boundary layer, it's an attached turbulent boundary layer, so it's following the shape around the aerofoil, even if that very small layer in contact with the aerofoil is a turbulent flow downstream of the turbulator. What we can also see that's nice to see is that the coefficient of drag is flatlining at the higher speeds, because we can't take the wind tunnel up as fast as it's possible to fly a hang glider. So this data cuts off at 15 meters per second, which is about 50 kilometers an hour. So it's a little bit faster than trim speed. A bit faster than trim speed. It's it's probably around your best glide speed for a lot of gliders, but you will often be flying quite a bit faster than that. But because we can see that the coefficient of drag is flatlining at those speeds, it's probably a fair bet that it's staying fairly flat out to those higher speeds as well. So we can treat the coefficient of drag as constant at those higher speeds, which is very useful for calculations and for prediction of performance. The cylinder that we're measuring this off here, this isn't an upright size actually. This is the larger size, the cross tube size for the single surface cross tube. So it's actually about twice the diameter. But of course, because these are coefficients, these aren't the absolute values. It's fine to compare them like that. I've corrected for that in the cross-sectional areas. But now if we look at the force, at the absolute force per unit length, obviously it doesn't make sense to plot those directly against each other now. So what I've done with this graph is that although the values for the speed and for the rubber backed upright, so the raw values that would come off the rig, the value for the cylinder now is corrected by scaling it down to the diameter of what a round upright would be, so 1 1/8 inch tube. I think it's fine to do that in this case, because you could see that the drag coefficient, especially for the cylinder, was pretty much flat, and also because that drag coefficient did so nicely match the textbook value, I think we're pretty good on this. Now looking at this force data, it's good data. You can see that obviously the force increases as you go faster, which is obvious. It increases roughly with the square of speed, but not exactly with the square of speed, which is because the drag coefficient isn't a constant. So in the earlier videos when I said the parasitic drag increased proportional to the square of speed, well, that's roughly true, but in real life these mathematical approximations don't always hold exactly, because that was assuming a constant drag coefficient, and you could see from the previous graph that the drag coefficient isn't actually constant. What this graph does show quite nicely is just how much lower drag the aerofoil sections are than the round section. As I say, we don't actually offer the round sections anymore. Our basic gliders have the rubber back ones. But you can see that compared to a round section, well, the round section is about 4 times more drag than the speed section. The rubberback section is about 30% more drag than the speed. And bear in mind, this isn't going that fast either. This is only 50 kilometers an hour. And obviously, the faster you go, the more penalty you're paying for that increased parasitic drag. So now we've got the values per metre of the amount of drag that each one of these components is making. Obviously, what we're really interested in is how much difference does it actually make into the way the glider flies. So this was my main motivation for doing this. It was mostly to improve the accuracy of my simulations and my predictions so that I can be doing more accurate modelling. I've already been simulating the wings in OpenVSP, so that's a vortex lattice model, and although it lets you draw in the other components as well, I always turn those off when I run the analysis and just do the analysis on the wing on its own, because really it's not going to give any kind of meaningful results on the turbulent separated flow you get around these kind of components. But by having the model for the wing and then including the real life data for the control frame, I can start to improve the accuracy of this. So I've plotted some of this data then. So I'm using the data from the vortex lattice analysis of the Puma wing. So this was using some actual scan data for the shape of the wing, modelling in OpenVSP and getting some results out of it. So if we look at the lift to drag ratio as a function of speed, I mean you can see it's unrealistically, or it seems unrealistically high for a hang glider. You've got a glide angle there of 19:1, which I bet we'd all love, but of course this is just the wing. This is without any pilot, control frame or wires. But now of course we actually have that data, we can start adding this in. So let's see what would happen if we put those round upright, a frame that's made of round uprights. So we know the length of the uprights are 1.65 meters, know the length of the base bar, that's about 1.3 meters. So you put in enough length of that round tubing and add in the effect of the parasitic drag from that, and you can see it nails the lift drag ratio. So I mean it's still respectable in that it would be gliding at best somewhere around 14:1, but you've got to remember this is still without the pilot, still without the wires on it. So let's see the effect that if we put the rubber backed upright frame in. So this is the two uprights with the rubber back section, but it's also the base bar with the round one. So, and that's the lift to drag ratio as a function of speed that you'd get if you just had the wing and the rubber backed frame without the pilot, without the wires. And now our best glide is somewhere around 16ish to 1, 15.96. So yeah, probably about 16:1 in the middle there. And with the speed frame on, then you can see that now we're getting somewhere. This is lift to drag ratio of 17.1. Of course, it's going to get knocked down a lot further than this when you've got the pilot and when you've got the wires in. But it probably shows that actually those vortex lattice models for the wings, because there's still quite a lot of parasitic drag to be added in there from all those other components, we're probably going to be getting down to about those kind of figures that we actually see when we're flying. But what this also lets you do, or what it lets you see, is that of course your best glide speed is at a slower speed when you've got more parasitic drag, which is obvious. It also gives us an indication of how much improvement in glide we can expect between the different frames. So yeah, with the caveat that there is still more drag to be added into that, and that's going to tend to, as you add the pilot and the wires and so forth, it's going to close all these together, these three together. But you can see that you've got about 17.4 as the best on the speed frame, 15.8 on the rubber back. So you've got about 1.5 difference between those. So when you bear in mind that you're adding in the other forms of drag as well, it will compress everything together, so it'll probably bring those down to less than a point difference between them, but still some difference. So that probably feels about right, actually, somewhere around a point on glide. Also bear in mind with all these figures, this would be in completely perfect still air. Now in reality, the days that we're flying hang gliders on, it's always a day when it's a thermic day, so the air's going up in the thermals. That means that on average all the air in between is always going to be going down. So most of the time you're flying, you're either going to be in lift or you're going to be in sink. Even if it feels like dead air, there's probably still a little bit going on, so it makes it very difficult to get these numbers experimentally. We can also plot this as polar, and you can kind of see the same basic trend. So yeah, wing only, and then when you add in the effects of the control frame. So I found this project really interesting because although those results that I've shown you so far, they're all broadly as we expect, it's really good to have that confirmed and to have those precise numbers to nail these things down, which will be really useful going forwards to put into the simulation and the optimization, because of course the next gen glider will still have the same control frame. If you want to see more about how we're getting on with that prototype and on the development work, then have a look on the Patreon site as well. There's a lot more on that. And we also were trying some other things with this wind tunnel, so I'm going to do another video hopefully fairly soon that will show what we were getting up to with that, because that wasn't so much the results I was expecting. And finally, just really big thanks. Thank you to Will for doing the final year project, and well done on the project, Will. Thank you to Dr. Simon Hayes in the Department of Aerospace Engineering for supervising this project, and thank you to the University of Sheffield and Department of Aerospace Engineering.